Hey everybody, it's Thursday, October 1st. As you can see on the screen, the aim for today is to use graphical relationships to define speed. Now, as it turns out, graphical relationships are extremely important in this course, not just for motion, but really for all topics. And so we are going to use it a little bit now as we continue to move forward and talking about motion. At the very end, we are going to go and wrap it up by basically taking a more detailed look at motion graphs. And then, as you'll see, when we go through the concepts for the rest of the year, you'll see all of these things pop up again and again and again. So over the next week or two, it's very important for everybody to pay close attention to the things we're saying about graphs. So, the first thing we want to say here is about how to read a graph. So when you are analyzing a graph in physics, you really only have to ask yourself one question when you're looking at the graph. And that one question is, as the x-axis variable is increasing, what is happening to the y-axis variable? Is it increasing? Is it decreasing? Is it constant? Is it zero? And if it's increasing or decreasing, is it increasing at a constant rate? Is it increasing at a changing rate? Et cetera, et cetera. Take a second to pause this video to write that down because that's super important because we are going to be reading graphs all year long. Okay, so we want to put this to the test. And so to put this idea or this skill to the test here, we're going to take a look at a couple of distance versus time graphs. I'd ask you to start sketching this in your notes as we're going through this. So here we're going to take a look at 4 different distance versus time graphs. And essentially, once they're drawn, I'm going to ask you if you would take a moment to pause the video, try to interpret the 4 graphs, write down that interpretation, and then we'll talk about them. So take a second to sketch those axes here. And so now we'll go ahead and we'll sketch our graphs. And so for this first graph, and we're going to label these before we draw them, just so we're all clear about what we're talking about. We're going to label this one number 1, this one number 2, this one number 3, and this one we're going to label number 4. And so for the first one, we're going to draw a graph that looks something like this. So just a straight horizontal line. For graph number 2, we're going to draw something that looks a little like this. So just a straight vertical line. I'm going to try to make this a little bit thicker just to ignore that part that I messed up. So we just have a straight vertical line here. For graph number 3, draw something that looks like this. And for graph number 4, we'll do this. Okay, so now that you have these graphs drawn, I want you to do 2 things. And the 2 things I want you to do are right here. The first thing I want you to do is read the graph and interpret for distance. So what's happening to the distance and what does that really mean? And then 2, what does that tell us about the object? And specifically about the object's motion. So take a second to look those over, pause the video here, answer those 2 questions, write them out in a list, 1, 2, 3, 4, and when you hit play, we'll go over it. Okay, so remember what we said here is to read and interpret the graph, you have to ask yourself the question, what is happening to the y-axis variable as the x-axis variable is increasing? And so looking at the graph, since the x-axis variable is time, you would ask yourself, what is happening to the time what is happening to the distance as the time increases. And I think looking at that graph, it's pretty clear that the answer is as the time increases, the distance remains constant. And so the question is, what does that really tell us about the object? If the object has a constant distance, what does that mean? Well, as the time is increasing, the distance remains the same, meaning the object is not moving. The object here is at rest. So since the distance is not changing, we know that the object is not going anywhere. Moving on to number 2, and I'm going to go back to this page here. It says for the distance versus time graph for number 2, we have this straight line going up. And so the first question is to read and interpret that for the distance. And remember, all we said you have to do is say, as the x-axis variable increases, what happens to the y-axis variable? So as the time, and the time is not really increasing, but the distance is. The distance is increasing when no time has passed. What does that tell you about the object? Okay, I promise this is the only time I'm going to do this to you this year, but this was a trick. I wanted to see if you were thinking. Number 2 is physically impossible. If you remember from math, a vertical line has what they call an undefined slope. And so that's important here because that's not physically possible. The fact that the slope is undefined actually has a physical meaning. And it means here that that kind of motion is not possible. It is impossible for an object to travel a certain amount of distance in no time. So graph number 2 is physically impossible. Moving on to number 3. Number 3 is a very important graph for this year. And as we said, to read and interpret this graph, you ask yourself the question, what is happening to the y-axis variable as the x-axis variable is increasing? So as the time is increasing, the distance is, and I think it's clear to everybody that the distance is increasing. But what's important about this graph is not just that the distance is increasing, but it's about how the distance is increasing. And so here, the fact that the distance is increasing at a constant rate is the important part. And so the distance for number 3 is increasing at a constant rate. So as the time is increasing, the distance is increasing at a constant rate. We can tell that, by the way, that the distance is increasing at a constant rate because the slope is constant. And the fact that the slope is constant is how we know that distance is increasing at a constant rate, because slope means rate of change, which I know you must have seen in math by now. And so what we're saying here, to interpret that for how the object is moving, we're saying so the object moves the same distance every second. And we're going to come back to this one in a few minutes. Let's just go ahead and finish up number 4. Number 4 is basically a combination of 3 and 1. First, the distance is increasing at a constant rate, and then the distance stops increasing. And so essentially what we're going to say here is the object moves equal distances in equal times and then stops. This, we'll say, is a combination, I'm just going to write combo because I'm going to run out of room, of numbers 1 and 3. Let's take a second to write one quick note here. And that quick note is going to be straight lines on a graph tell us that the slope is constant. It could be positive, 0, or negative. When the slope is positive and constant, it tells us that the y-axis variable increases at a constant rate. That's going to be very important for the whole year. Take a second to pause this video, write that down, and when you hit play, we're going to dig into graph number 3 in a little more detail. And with that, I'd like to take a deeper look at graph number 3. As we said, graph number 3 is a graph that shows a straight line. And this is a graph which has a straight line with a positive slope. So this slope, and I want to write this down because this is important, this is a constant positive slope. And the fact that the slope is constant and positive is important, as we said, because that tells us the distance is increasing at a constant rate. Now, an important thing to realize here is that this has a lot of importance in physics. In physics, the slope of a graph has what we call a physical significance, which means that the slope actually means something in real life. It tells us something important about the graph. And if the graph is describing a motion of the object, we could take that one step further and say it tells us something important about the object's motion. Now, this note here, the big note, is one of the most important notes we've seen so far this year. Extremely important. Everybody write that down. To determine the physical significance of a slope, you divide the y-axis units by the x-axis units. In this course, as we said, every single physical quantity has its own unit. And so if a slope has a particular unit, and we know that that unit is the unit for a physical quantity, then that tells us the slope represents that physical quantity. So we can't go too crazy about the examples here, but I hope everybody knows that distance and displacement are measured in units of meters. So if we find the units of a slope, and the units of the slope happen to be meters, then that tells us that the slope represents the distance or displacement, because only those variables are measured in meters. And that's the idea. Now, the key thing I want you to focus in on here is that you're taking the y-axis units and you're dividing them by the x-axis units. And I feel like a lot of people, when I usually say that, try to memorize that. We're not doing that for no reason. The reason why we're dividing the units is because the slope formula tells us to divide the units. So I'm going to write over here, that's what the slope formula tells us to do. I'll write slope equation. That's what the slope equation tells us to do. And so that should make a lot of sense. If we want to find out what the slope means, we just apply the slope equation and divide the variables. We can also divide their units. That's the idea. So let's revisit that graph. This graph is a graph of distance versus time. And as we said, distance is measured in units of meters. Time in physics is measured in units of seconds. So let's talk about how we can find the significance of the slope. Well, the first thing we do is we take our slope equation. The slope, which remember from math gets the symbol m, is delta y over delta x. And so that tells us the slope units can be found by taking the y-axis units, which are meters, and dividing them by the x-axis units, which are seconds. And so we can say here, the slope has units of meters per second. Now, of course, the big question here is, if the slope has units of meters per second, what does that mean? If I tell you the measurement is 5 meters per second, what is that actually telling you? Well, it's telling you how many meters something goes in a second, but what is that a measurement of? And the point here is that since the slope has units of meters per second, so the slope represents speed. It tells us how fast the object is going. That's the idea. So, to summarize, since the slope of a distance versus time graph has units of meters per second, and the physical quantity speed has units of meters per second, the slope of a distance versus time graph represents the speed of the object. That's a super important point. You would be crazy to not write that down. Now, the second point we want to make here is what we just did with the slope formula doesn't just apply to the units. It also applies to the variables on the x and y axis. So what I wrote here in the second note is we can also use this idea to write an equation for speed. And that really is one of the more important features of this slope idea, that instead of just writing a sentence where we say the slope represents this thing, it also allows us to write an equation for speed. So what I wrote here is, instead of just dividing the units, we can divide the y-axis and x-axis variables to write an equation for the thing the slope represents. And we're going to go ahead and do that now. So if you haven't finished writing this down, take a second and pause this video. And when you hit play, we're going to take a look at an equation for speed. Okay, so you should be writing this down under the heading average speed. Now, notice I haven't used the word average so far, but I'm going to use the word average from now on. If you remember from math, they should tell you slope represents the average rate of change. Now, we don't need to go too nuts about this average idea when we're just looking at straight lines on graphs, because the rate of change is constant. You can tell it's constant because the line is straight. But when we're talking about slopes, really what we're talking about is the average rate of change. And so here, we are going to report that by talking about the average speed. So looking at that graph, we took meters divided by seconds, and we got that the slope represents the speed. The important thing to realize here is that the y-axis variable measured in meters was distance. and the x-axis variable measured in seconds was time. So since taking the units for distance and the units for time and dividing them, that gives us speed, well, we can just go one step further and say speed is distance divided by time. And that's shown to us here by this equation, v equals d over t, where d is the total distance, t is the total time, and v is the average speed. But notice the way the units work out, right? We take distance in meters, we take the time in seconds, we divide them, we get meters per second. That's pretty straightforward. An important thing to realize here is that I wrote the words total for d and t. Sometimes you will just be given the total distance and the total time. Other times you'll be given separate distances and separate times, and we're going to take a look at both of those kind of problems before we wrap it up for today. Before we get to those problems, we just have to make one more very important point. Since average speed is based on distance, and distance is a scalar quantity, average speed, or just speed in general, is also a scalar quantity, meaning it contains no information about direction. They ask about this on the Regents. If I were you, I'd write this down. Since average speed is based on distance, and distance is a scalar quantity, average speed is also a scalar quantity, meaning it contains no information about direction. And this equation, v equals d over t, is actually the first equation that we've looked at so far this year that's in the Physics Regents reference table. So if you scroll all the way to page 6 on the Physics Regents reference table, and you'll notice this will now be in the Resources tab under Classwork, and you go to the last page, which is titled Mechanics, v equals d over t is the first equation under that list. Now notice on the reference table there is a bar on top of the v. I would guess that a lot of you have seen this in math, but what that bar means, when you write a bar on top of any variable, it means the average. So that bar on top just means average speed. You do not need to write that when we are doing these problems. I just wanted to let you know what that meant. Okay. Take a second to write this down if you haven't already, and when you're finished, we'll go ahead and take a look at a problem. Okay. This question is in the 1D motion packet on page 4, number 27, if you want to look at it separately. And it says, a high-speed train in Japan travels a distance of 300 kilometers in 3.60 times 10 to the 3 seconds. What is the average speed of this train? So let's go ahead and take a look at how to solve this. Okay. So as is always the case, the first thing we do whenever we solve one of these physics problems is we write down the information they gave to us. They told us the distance is 300 kilometers, right? And they told us the time is 3.6 times 10 to the 3 seconds. So they told us the time here is 3.60 times 10 to the 3 seconds, or 3,600 seconds. And they're asking us for the average speed. This is a really important tip. Every single year I see this. I give a problem very similar to this on the test, and this is what everybody does. They write down their knowns. They take 300, that's the distance, divided by 3,600, that's the time, and they write down the answer. They forget about the units. They go to the answer choices, and they circle the answer with the right number. That will get you the wrong answer. It's an important thing to realize that. Notice all of the answer choices are given in meters per second, not kilometers. So you have to convert kilometers to meters before you can do this problem. That's why I showed you how to do that already. So remember, when we're just going to meters, we don't need to go nuts. We can literally just replace the abbreviation for the prefix with the appropriate power of 10. So we write 300, and then we have times 10, and kilo, if you remember, I hope so, stands for 10 to the 3. And so that means this distance is 300 times 10 to the 3 meters. But wait, that's not written in correct scientific notation. And it's not written in correct scientific notation because this number out in front needs to be greater than or equal to 1, but less than 10. So this is saying from here, you have to move the decimal point 3 places to the right. But we need the decimal point to be here for the number 3 to be greater than 1 or less than 10. And so notice, if I move the decimal point there, I would have to go 1, 2 places just to get it back to where the decimal point is now. So that means I just have to add 2 to the exponent, making this number 3.0 times 10 to the 5 meters. Now we're all set up to use our equation. So the equation for average speed is v equals d over t. And I have my distance, 3.0 times 10 to the 5 meters, over my time, 3.60 times 10 to the 3 seconds. And when you do that math, 300,000 divided by 3,600, you get 83.333. Repeating, which we'll just round off because this was given to 3 digits and this was given to 3 digits. We'll just call that a nice even 83.3 meters per second. Of course, if you were confused, how am I supposed to know that I'm supposed to round this to 3 digits? Don't go nuts. Just look at the answer choices. The answer choice is rounded off as 83.3 meters per second. So that's it. The answer here, and you don't have to write this, I'm just going to write it just because. The answer here is choice 4, 83.3 meters per second. Now it's important to realize the Regents is written by evil human beings. And what those evil human beings do is they prey on your every mistake. As I mentioned, a common mistake here is to forget to convert the distance. And look at what happens when you forget to convert the distance. So remember, we had 300 kilometers. So if you just took 300 and didn't pay attention to the unit, and you divided it by the time, which is 3,600, you would get 0.0833, which is 8.33 times 10 to the negative 2. They gotcha. They really want to keep you on your toes. Conversely, if you took 3,600 divided by 300, if you accidentally flipped them, instead of doing d over t, if you did t over d, you would get 12, which is choice 3. And if you did correctly do the conversion from 300 to 300,000, and you accidentally divided the time by the distance instead of the distance divided by the time, you would get choice 1. So here, the way they are writing these answer choices is they are giving you every answer choice that represents the most likely mistake you would make. This is why I have been talking so much about problem-solving procedures. So you really want to make sure you're on your toes when you're doing these problems. Let's just take a look at one more problem quickly before we go, and that'll be it for today. So this problem, which is on page 2, number 14, says in a 4-kilometer race, a runner completes the first kilometer in 5.9 minutes, the second kilometer in 6.2 minutes, the third kilometer in 6.3 minutes, and the final kilometer in 6 minutes. It says the average speed of the runner for the race is approximately. Now notice here, they do give you the total distance, but they give you the times separately. And when we wrote the equation v equals d over t, we had total distance and total time. So before we're able to do this, we are going to have to find the total time. Additionally, despite the fact that the distance is in kilometers and the times are in minutes, and usually we do these problems in meters per second, if you take a look at the answer choices here, you'll notice all the answer choices are in kilometers per minute. And so actually, that's no big deal. All right, let's go ahead and take a look at how we do this. So obviously, as we've been saying all along, the first thing you do here is you write down all the information you're given in the problem. So they tell us this is a 4-kilometer race. They tell us the first time, which we'll call time 1, is 5.9 minutes. They say the second time is 6.2 minutes. The third time is 6.3 minutes. And the fourth time is an even 6 minutes. We are looking for the average speed. So the first thing we'll do is we'll just go ahead and find that total time. And so we have the total time is 5.9 minutes plus 6.2 minutes plus 6.3 minutes plus 6 minutes. Notice time is a scalar, so we just add them. That's pretty straightforward. And when we do that, we get 24.4 minutes. And now that we have the total time and we have the total distance, we're in business. We just use our equation, v equals d over t. And so v equals d over t gives us 4 kilometers over 24.4 minutes. And when we do that math, we get the speed is equal to 0.1639 kilometers per hour. And if we look at the answer choices, they have them all rounded off to 2 digits, so we'll call it 0.16 kilometers per hour. And that's it. That one's pretty straightforward, and that's about as annoying as they can be, just because we have to find the total time. So before we wrap this one up for today, I'd like you to just write down these 2 notes. The first note is always look at the units in the answer choices before setting up the problem. This part is very important because you don't want to waste your time converting all the units, getting the answer, and then realizing you have to convert it back to have it fit the choices, right? And the second note here is average speed is always the total distance over the total times. And it says if the times and distances are given separately, add them up first. And that's the only thing I want to say here that's not actually required. You don't necessarily need to add them up first. If you want, you can do v equals d over t and then write, like for that last one, d over t1 plus t2 plus t3 plus t4 and do it all in one step. That's entirely up to you, just as long as you're writing all those things in your list of knowns and showing it all appropriately, it's up to you. All right, everybody, that's it for today. Now that we finished up average speed, we're ready to get into talking about its analogous vector quantity, which we'll do tomorrow. Have a good one, everybody.